Okay.
Hi, everyone. Welcome to this week's Assaf seminar, episode 31. Today, we are very excited to host Assaf Ben-Kish, a PhD student at Tel Aviv University and a visiting researcher at MIT CCL. Assaf's work focuses on non-context modeling, especially with recurrent architecture like Member. He's the creator of DESI Member, the first context extension method for Member models. In today's talk, he'll share insights into the memory bottleneck of recurrent large language models and introduce OPRM, a new method that significantly boosts performance on non-context benchmark like non-bench. Let's give a warm welcome to Assaf. I'll hand it over to you.
Hey, thank you, Songling, for the introduction and also for inviting me for this talk. Today I'll present our most recent work, which is called Overflow Prevention for enhances long context recurrent models. It was recently accepted to Colm. And what are overflows? How do we prevent them? And why does this enhance long context models? I'll try to answer these questions in the talk. And before I begin, I want to thank also my collaborators on this project, both from Tel Aviv and MIT and IBM. So we're in the long context domain. Long sequences, they're all around us. They have many forms and shapes, like books, large code repositories, and long audio and video data. And we know that transformers, that they're state-of-the-art for short sequence processing, but when they are applied to longer sequences, they pretty quick become limited because of their quadratic complexity. Now, to overcome this limitation, there's a few research directions in recent years. Some of them are transformer-based solutions, like flash attention and NSA. But today we'll focus on a different line of work, which is called subquadratic recurrent models, which basically diverges a bit from the classic transformer architecture. It's more similar to RNNs. And because they have a very efficient design, they're good candidates for long context processing. Some of them you might know are state-space models, DeltaNet, RWKV, and so on. So when we started this project, a few very strong recurrent LLMs started to appear. For example, we have Falcon Mamba 7B, we have Recurrent Gamma, we have RWKV. And we see that these models highlighted in blue, they are already competitive with transformer-based models, here highlighted in yellow. So we see here leading models like Llama 3 and Mistral and Gamma from Google and so on. But the thing is that these benchmarks, which are very popular, are only for short context processing, and we see that the average sequence length barely reaches the 100 token length, which is maybe even ultra short. And this is a good first step, but we want to see what happens in longer context. So what happens in longer context? We tested one of these strong models, Falcon Mamba 7B, and we took a long context benchmark, Hotpot QA from Longbench, and we evaluated it in two settings. The first one is the baseline setting. We just process the model as is. And the second setting, we call it random, where we kind of take the full sequence and we select a random chunk. We give it to the model and it processes only this chunk, and it's kind of blindfolded to all of the other parts in the sequence. And to our surprise, we saw that our random method is already improving the baseline model. And as we increase the context length, it actually becomes better. So at this point, I can stop because I already gave you a way to improve your recurrent LLM. But because this behavior, it's very, very weird, we kind of tried to understand why does it behave so weird, and why does the random method work better than the baseline? And we can see that the model kind of behaves nice in some range, and then suddenly there is this sudden drop in performance, which kind of gets even worse when we increase the sequence length. So why is this happening? Now, it's important to say that this doesn't happen only for a hotpot. It happens for most of the benchmarks we tested with many other models. And there's a clear gap, performance gap, between these state-of-the-art recurrent LLMs and transformer-based LLMs, which is still not closed. And it's quite surprising because these strong recurrent LLMs, they already have these good conditions to be good long sequence models. For example, we saw earlier, they match state-of-the-art transformers on short sequence tasks. Their parameter count, it's large enough for in-context learning. We saw 7 billion parameters. We know it's enough. Their hidden states are very large, so we expect them to memorize a lot. And also they were trained on very long sequences that are even longer than the benchmark we evaluated. So for example, length generalization is also ruled out here. So we ruled out a lot of things, but yet these models still do not, there's still this very large performance gap that we are not able to close. And in order to understand why this happens, we took let's explore the perspective to understand why this happens. And we kind of investigate the recurrent memory capacity of these models, which in other words, it means we want to test whether recurrent LLMs are able to store and later retrieve all relevant information in a long context. In order to do this, we go to the associative recall task, which is AR for short. You must have heard of it before, but if not, it's defined as the ability to learn and remember the relationship between unrelated items. And it's a crucial capability for strong language modeling. For example, if I have a story and I have characters in the story, Alice and Bob, and I want to remember their professions, for example, Alice is a lawyer and Bob is a doctor, I need to have some kind of lookup table that remembers these associations between the character and the profession. And here we can also, what's nice is that we can measure, we can quantify the associative recall performance by this synthetic task. I took a sample here, for example. So we have these key value pairs in the context, K1V1, K2V2, and so on. We also have like padding tokens because we want to control for the length. And then we have a Q, which is the query. It's equal to one of the keys. For example, if the keys are the names and the values are the professions, then Q, for example, can be Bob, and then the model's job will be to retrieve the correct value, which here is a doctor. So how good are state-of-the-art recurrent LLMs in associative recall? So we took the strongest recurrent LLM, Falcon Mamba 7B, and we found out that this model is not very good at associative recall. We were actually surprised by how bad it was because it has a very, very big hidden state. Yet we found two things that were very interesting. The first one is that the performance, the memory capacity was significantly smaller than we expected. It was able to save maybe 30 key value pairs, not more, which is a really small amount. And the second thing that also kind of surprised us is that the performance is degraded really fast. We see here that for 20 key value pairs, we have an accuracy of 80%. We are jumping up to 120 pairs, which is not a lot of information. We see that the model completely collapses and it barely remembers anything that it saw in the context, which is a very weird behavior. And also what's interesting is that every data point in this graph is 1,200 tokens long. So this means this happens in short context. So this model, this phenomenon, it doesn't even have to relate to long context, it relates to something else. We term this behavior recurrent memory overflows and in short RMOs, and I'll just use this here and there during this talk. And we said that this phenomenon is quite different than things we've seen before, and we claim that it is a fundamental long context limitation. Why? Because we see that it is not sensitive to other factors, for example, the sequence length. And we see that it's mainly correlated to the information content within the sequence itself. So to show this, we repeated the same experiment. We have the green curve. It's the same curve we saw before here with exactly the same curve. This is for 1200 tokens. For the purple curve, we have 300 tokens in each data point. For the red one, we have 4800. So we kind of really vary the sequence length. And we see that this barely changes the profile of the memory behavior. And mainly what dictates the performance is the information content within this context. So we kind of need to find out a new solution that will take care of RMOs, because before we didn't really have these solutions that we're looking to completely fix RMOs. So how do existing solutions look? There are two directions that have been before. One of them is that we can increase the state size. We saw it in Mamba 2, XLSTM, HGRN2. We saw that this improves performance, so we can do this. A second one is that we can also manage the memory more effectively. For example, DeltaNet, where it has these elements in the architecture that can also take out information from the state. So this is a bit more effective management. There are new approaches like log linear transformer, which expand the state with some predefined ratio of expansion of the log law. But here in this work, we didn't talk about log linear attention. And we ask, are these approaches, are they enough to solve the recurrent memory overflow problem? And we claim that this is not enough, and we show it through an experiment. So here we took a two-layer toy Mamba model, and we played with it hidden state size. So in Mamba, the hidden state size, it can be, it is the channel dimension times the SSM state dimension. So here the x-axis is the channel, and the y-axis is the state dimension. And in each point is a model that we trained for associative recall with this state size. And we retrieved all of these models to retrieve 128 key value pairs. And we see here for each model, if we go right or up, we increase the state size. So its recurrent capacity should improve. And what we see here at each point is that this indeed happens. We see that there is a scaling, that there is a kind of a scaling trend as we move along the diagonal. And we see that we're able to increase the memory capacity, which we define the maximal amount of facts that were in the context over 128, which is the amount of facts we wanted to retrieve. But we see that it never reaches one. It never, if there is, it's for an arbitrary information content, we will not be able to satisfy this, we will not be able to prevent these recurrent memory overflows. And if we kind of zoom in on what's happening, let's see what happens when we increase the state size from 64 to 128, which is this one to this one. Mainly what we do is we kind of stretch the associative recall curve, but we don't really change the profile. We're able not to process 4, we're able to process maybe 16, but when we have 128, we will still suffer from these recurrent memory overflows. So we conclude from this example that if we statically allocate the recurrent memory capacity before pre-training, we're going to suffer, it's not going to be robust to recurrent memory overflows. So to this end, we propose OPRM, which is short for overflow prevention for recurrent models. OPRM is a training-free inference algorithm, and the motivation is like malloc. You know, in C, we have malloc. We want to dynamically be able to allocate more state as the information content increases. So how do we do this? We have this associative recall curve that we saw before. And the motivation is that we're in token number 1. We are in the beginning of the sequence. We didn't compress anything. And then as we go on in the sequence, we will eventually reach this point where we'd want to stop compressing information. We'd want to take this state, put it aside for a while, and then allocate a fresh state so it kind of will reset the working point of the recurrent memory capacity. And then this will fill up, and then we'll store this one aside, and then we'll have kind of a dynamic mechanism for storing in-context information. So how does the OPRM work? We have two stages. It's very similar to the stages in typical inference. We have prefill and decoding. We change the prefill, we call it speculative prefill, and we change the decoding, we call it selective decoding. They're all small changes such that we will be able to take care of overflows as well. So how does it work? First, we have a small pre-processing step. Here we receive a long context. It usually has the structure of prefix, context, and suffix. Prefix can be like the beginning of sequence token, and then we have like maybe a pre-query before the context, like please read this book. And then we have the context, which can be the book. And then we have the suffix, which can be, for example, a question about the book, like which one of the characters is the lawyer. And then we take this context, and the first thing we do is we chunk it into chunks. I'll soon tell you how we chunk it. And then we take these chunks and we concatenate to each chunk the prefix and the suffix such that it is kind of a sub context. It's only a part of the context, but it's still contextualized with the query and the other important tokens. And then we process all of these tokens in parallel, which is the speculative prefill phase. So here you see we have B chunks, and then we process all of these B chunks together. You can think of this as the batch dimension. So we just have this, we process the whole thing in parallel. And then what we get when we process in parallel, for each chunk, we can save its recurrent state, the final states. We call it HI. So here for chunk 1, we have H1. For chunk B, we have HB. And we also keep the output probabilities for the first decoded token because we will use them later. The second part is selective decoding, because and here we have this kind of assumption that one of the chunks will hold the answer. And we have the main part is here that we want to select the best chunk for decoding. And once we select this chunk, we load it to the GPU memory, and we just decode it and we predict our answer. Questions? Okay. So let's talk a bit more about how we do selective decoding. So how do we select the best chunk? So we have two parts in this phase. The core of the method is around the entropy-based selection. The idea is we want to select the chunk that the model was most confident about. So we compute the entropy over the output distribution for the first token. And the lowest entropy, we assume that this is the chunk that the model was most confident about. It has the answer, so it's not confused by the query. And then we will select this chunk. But if we do this, we have a problem. It won't work many of the times. And this is why we have this additional component, which is called the IDK filter, which is short for I don't know, like when we type in the chat. And let's see why we need this component. So let's say I have a strong model, and this model is calibrated. So it knows quite well if the answer does not exist in the chunk, it will be very confident that it doesn't know the answer. So if I have a strong model, then let's say for the first chunk x1 that doesn't have the answer, if it will be very confident that it doesn't know, I will select this chunk. And then when I decode it, I will get not enough information to answer, or the provided text does not hold enough information. And we kind of want to get rid of these chunks because they are noise instead of selecting the correct chunk. So how can we solve this? We can actually have a very simple prompting technique that can solve this. So let's say we have a query. We have this question, like which town near this border is this Lancashire Mill located? It's just a geography question. And all we need to do is just add to the end of the question, if the answer is unknown, respond error. So now if the model gets this chunk, and it is confident that it doesn't know the error, the answer, it will predict the error token. And we take all of these chunks and we just filter them out, and we just stay with the entropy-based, and then we stay with all the interesting chunks, which we pick with the entropy-based criterion. Let's see an example. How does this work? So I gave here we took this query from Hotpot QA. It has 8,000 tokens in it, and somewhere the answer is inside there, and it's bar nodes weak in this case. And let's see what happens when we just take the vanilla model and we the recurrent gamma 9b, which is kind of strong, and we let it process the context as is, and it just repeats the question. It doesn't really know the answer. We assume that it suffers from recurrent memory overflows. It kind of maybe it read it and forgot, and now it's not able to retrieve it. If we apply OPRM, then what happens is that the model predicts the provided text does not contain any information regarding a meal or its location, so I cannot answer. So we see here that the model was very confident it doesn't know in one of the chunks that the answer was not there. And when we add our special filter, the model is able to discard these additional and non-important states, and it's able to predict the right answer bar nodes weak. So last thing about OPRM is the chunk size. We kind of experimented a lot with trying to find a way to quantify the amount of information inside the state. And after a lot of experimentation, we kind of went to the heuristic where we just have this hyperparameter of a constant chunk size. We saw that it works really well. For example, 3,000 tokens. You have a small validation set, you kind of tweak it, and then you find your best chunk size. And we see it's robust, it works well in practice, and it generalizes really easy to all recurrent architectures. So just we're left with this thing. And that's the whole method. Any question before I move to the results? Okay. So let's see the results. So for the synthetic test, the associative recall, we can see that we're able to change the memory profile. So now the associative recall curve, it's flat, it's able to scale with the information content in the data. And now we practically solved the AR task for this model without any training. The second thing, if we move to long context real world tasks like we saw before with Hotpot QA, we see that there is a very big significance on the chunk selection. We see here that the same one we saw before with baseline and random, we see that with mean entropy, the criterion that we introduced, we're able to significantly improve the results, especially when compared to the baseline. We did some extensive evaluations of this method. So for example, in Longbench, there is 16 different tasks, single document QA, multi-document QA, summarization, few-shot learning, and so on. And we see that for a variety of leading recurrent LLMs like Falcon Mamba, Falcon 3 Mamba 7B, Recurrent Gamma 9B, RWKV6, we are able to increase the performance on average by 35%, which a result we were very happy with. And also one thing that was kind of popping out when we did these experiments, we found out that in multi-hop reasoning, we were really able to improve the results by a lot. We can see here that here's the 2, 4, and 5 hop benchmarks from Longbench. We see in some cases we even doubled the results. And the thing is that for multi-hop, we really need this associative memory to work very well, because if I have, for example, 2 brothers and one of the brothers is a lawyer, and then I ask a question about the brother of the lawyer, I kind of need to remember all of this reasoning trace. And the AR is exactly the right task for all of this association memorization. So we saw a very big leap in these kind of tasks. What's also cool, we evaluated our model on ultra long, long context benchmarks like Longbench V2, which reaches up to 1 or 2 million tokens. And we see here that our Falcon 3 model, Mamba, with OPRM, actually achieves state-of-the-art results on this benchmark for its size class when compared to transformer models. We see in the ultra-long context, transformers do have a problem. And it was really cool. I think it's the first time that actually a recurrent LLM was able to match transformer models in these long context benchmarks. And also we see this in other benchmarks. For example, the Infinite Bench, which has up to 200,000 token sequences. We see that the base model, Falcon 3, it has only 12.2. And when we add OPRM, it triples to 36.5. And it's able to beat some leading transformer-based models like Mistral with a context extension method. And it's also competitive with much larger proprietary models. They're not the state-of-the-art models today. This data was taken from the paper, but Claude 2, I think it's very good news that these models are actually able to rival these transformer-based models because they have something in the architecture that makes them more scalable. Okay, so we just talked about performance. Let's talk about efficiency. Efficiency-wise, we see that OPRM is faster. These two rows. We see that for 128,000 context lengths, with OPRM, the speed gains we were able to be 10 seconds faster than the baseline. And the reason is that speculative prefill, it allows us an additional dimension of parallelization over the sequence dimension, which is usually what people don't do. But here we have a really good motivation to do this. So this also translates to speed gains. And also what's really cool is that the additional space required for OPRM is quite negligible. And the reason is that if we compute the amount or the state size, the amount of space that a state needs, the activations, compared to the space that the weights need on the GPU RAM, it's 3 orders of magnitude smaller. So this makes us feel kind of we can freely allocate more states, and it will barely help us, and it will barely increase our memory usage, which is quite nice. We also show that overflow prevention is very good for context extension. It naturally performs context extension because it kind of stops at some point and then it continues from a fresh state. So it also zeroes the token count, not only the information count. And we see that OPRM actually beats those dedicated methods by a large margin. So for example, here we have the Mamba, which is our previous work for context extension. We train it for needle in a haystack, and here the x-axis is the context length, and we train it on 2,000 tokens, and it's able to generalize up to 128,000. OPRM is actually, without training, able to generalize up to 500,000 tokens. And we also see this in real-world long context tasks. For example, Decimamba and Long Mamba, which is follow-up work. If we apply OPRM on a Mamba 1.4.b model, which was trained on tokens of 2,000 tokens, and then test it on Longbench, which has 8,000 or 10,000 tokens on average, it does better length generalization also on all of these real-world long context tasks. And the motivation is that if we do overflow prevention, we don't need to do context extension because it happens naturally. But the other direction, it's not true. Because if we do context extension, we just let the model process more tokens, but we still try to compress them into a fixed size state. So this means that we will still suffer from overflows, and therefore we will not benefit we will still suffer from these overflows that will degrade performance. Yeah, there's more things here. I'll jump to limitations.
Yeah,
So-
Assaf, would you mind if I ask a quick question?
Yeah.
Cool. One thing I wanted to know is, did you guys try this with transformers?
Okay, so we haven't tried it with transformers, but the motivation for transformers is different because it memorizes the whole sequence. So we don't expect it to have recurrent memory overflows, but we didn't explicitly test it.
The reason I was asking is because if you cut up the transformer context into all these little chunks, then you no longer have the problem that transformers have that leads to the reason people use RNNs, which is the, n squared timing.
It's true, and I think it's a good question, and I think this really talks about how this is like a first step to understand why recurrent models fails, and it doesn't necessarily want to improve transformers. And I think the lessons from here, I'll talk about it in the end. Here, if we're able to increase the memory capacity, and we're also able to add some more things for the overflow prevention methods, then you will kind of get a very efficient architecture that can scale well and not need to break things into chunks and do stuff that are a bit more unnatural. But breaking into chunks is I think, a well-known approach, like agenting stuff. When you play with ChatGPT, I think it does it when you give it a document or something. It's just another way to show how to scale recurrent LLMs.
Cool. I had a second question too, which is, it sounds like you guys choose just basically the top performer chunk at the end of the question once. Did you do any work where you, either combined different ratios of the states, or like, for example, if the information that you're looking for is spread into multiple chunks? I was just curious if you had any ideas on how to handle that, or where there are shortfalls there.
Yeah, so what I don't have the slide here, but we did have a test, for example, what you suggested, that what we did is that we did a two-step inference. First one is we use the OPRM metric to kind of give an importance score for each chunk. And then we concatenated the important chunks and then let the model process them in a second forward pass. So it's kind of like RAG. Here we have also a RAG comparison. And the thing we found is that it doesn't really help much. And it really goes down to this question of what's better, long context or RAG. And here, actually, these results, they show that if you choose smaller chunks, but a lot, it's not necessarily better. I can go into why, and I think these results also strengthen this thought, but we have tried and it haven't improved much. So what we think is that we should have some more complex algorithm to do chunk aggregation, and now we kind of want to leave it simple and training free, so we didn't experiment with it.
Cool. All right, thanks. Yeah, that's really interesting.
I have a quick question. So, have you ever tried using some RAG method as a baseline?
Yeah, so actually in this slide, we have two RAG methods. One is, here we have the baseline of Falcon Mamba 7B, and we have Dragon, which uses an external retriever. And here we have PRP, which uses an LLM to kind of rank the chunks, and then it selects the top K chunks. And then we have OPRM. And we see that OPRM actually beats these methods. And
do they have the same chunk size for each method?
So we controlled for what we did is that we controlled for the sequence length. So one OPRM chunk would equal, let's say if I have top 5, so we will have 5 chunks that are 5 times smaller. So the absolute value for the absolute sequence length for the RAG is equal to OPRM chunk.
Okay, I see.
And actually the reason that this happens is because there is works that try to investigate why long context is actually better than RAG. And we see that RAG usually doesn't beat long context, and it's because when you have RAG, you kind of select chunks according to how similar they are to the query. But if you have, for example, multi-hop, then some of the hops will not be similar to the query. For example, the example from before that we have two brothers, one of the brothers is a lawyer, and then I ask the question about the brother of the lawyer. Or something, you know, another one, like you have like these graphs and these intermediate jumps, they might not correlate as well with the query. And here you really need long context to use the whole context to understand that this is a hop that it's relevant according to all the past information.
Do you think your method could be viewed as a in-context RAG method?
Yeah, so we tried it for in-context RAG. Actually, it performed a bit better. So we had this two-step RAG method that, I described, that we kind of, the first time we used the mean entropy criterion to kind of rank chunks. And then we used another forward pass over the top 5 chunks. And then we saw that it is a bit better, but again, because of this hop hypothesis that we have, we think the results were quite similar and not a big improvement.
The interesting thing about this multi-hop is that you're relying on the information all ending up being in the chunk that you pull. And I could totally see how that's a very common outcome in real language because, you know, generally information is located near where you're looking. But I could imagine also scenarios where, like, you know, if you're doing code editing with an LLM, I can easily see that, you know, the associative important thing is going to be in maybe a different function that this function calls, and that function might actually be in a completely different part of the code base. And so I think in that scenario, it becomes interesting to kind of consider how you can achieve this multi-hop across chunk benefit, because I think otherwise it's going to be hard to achieve like what a transformer can in that scenario.
Yeah, I think there's a paper called GSM Infinite, and saying that, okay, for many non-context benchmark, like a non-bench, a RAG method could do very well. Like in your case, you try some RAG method, and they can do very well in such benchmark. But for those requiring truly multi-hop reasoning over the context, and those reasoning benchmark, this RAG method could perform really poor. Do you think your method would also inherit this kind of disadvantage of RAG method?
Okay, so just to say I understand the question, you think will my method with like the RAG flavor will perform well on GSM8 K infinite?
Yeah, there's a paper called GSM Infinite. Yeah, and for many benchmark like a ruler and the non-bench, these benchmarks are basically retrieval benchmark, and RAG method could perform quite well. And your method is some sort of like a RAG method, but with R encoder for each chunk. Do you think? But I think, like, high level speaking, this method is still a special case of in-context RAG. Do you think this method would also suffer from GSM Infinite, where the true in-context multi-hop reasoning ability is required?
Yeah, so I think it will definitely suffer there, because it doesn't have the cross-chunk processing capabilities. I think that what this work tried to achieve, we spent a lot of time to try to understand the recurrent memory overflow gap. And I think once we understand that we kind of have to use multiple states to have better models, this kind of opens a new trajectory for tackling exactly those kind of benchmarks that you said. Now the next, I think, as you said, like it's very interesting to see now what happens if we have a smarter aggregation method between chunks, because the information is there, we just need to retrieve it. My hypothesis is that you don't even need a lot of compute to do that, but it's like ongoing work. So this work does not solve this kind of complex, very long relation tasks.
I see. Thank you for explanation. I also have another question. So I think this method is mostly for pre-training, right? You cannot do, for example, like during the decoding stage, you cannot apply this method when you decode the tokens on the fly, right? Or you can still do the trunking method, like whenever you decode every trunk amount of token, you do a summarization. My question is, can you use this method for autoregressive decoding instead of pre-training?
Yeah, so actually, I think for the we played around a bit with how we can, maybe let's extract some part of the from each chunk and then concatenate them. Some places it worked really well, some places it wasn't. We think that the aggregation should be somewhere within the model, but you can definitely, I don't know, if you have like some reasoning or something that's very well separated, like summarization, for example, we saw that it really improved performance when you did that because each chunk is kind of self-contained and you can do these things. But yeah, it's kind of like it can help. We think that maybe some more an architect-wise solution will be like the best fit here. Did I answer your question? Maybe I didn't.
Yeah, I'm not sure if it answers my question. I think I'm curious because like for our model, one major application is like during test and scaling. This R model could offer much faster generation speed, especially in non-context. Yeah. And in such scenario, like pre-training stage is really cheap and the main bottleneck stays in the decoding stage. And I'm wondering, your this kind of like in-context RAG methodology could be applied to the decoding stage as well.
Yeah, so I think the only gain you can get in decoding is, if you want to kind of have a speculative decoding kind of thing, that maybe you will give every chunk some different weighting of the other chunks, and then you can try in parallel to compute all of the answers, and then maybe take the answer with the biggest probability according to some reference model or something. I think this can help you speed up things and test multiple solutions in parallel, but just speeding up decoding as is, I think it's difficult. I don't know if it will.
Yeah, because I feel like autoregressive decoding, it has a dependency across different trunk, and your method is mostly suited for pre-training, where you can divide and conquer those trunk and select the best one. Yeah.
Yeah, we were primarily interested in the pre-filling because we saw it didn't really work well, even when you really expected just spit out the right answer. We saw that even that failed. So this was kind of the focus on this work.
I see. Thank you. And I have another question. The title also mentioned overflow. Like, I think there's a paper called Stafford Member, and they show, okay, if you train on longer sequence, the model wouldn't suffer from the overflow issue. How do you think of that paper's opinion? And yeah.
So I think staff member, they talk about length generalization, which is the cases where your evaluation length is longer than the training length. And this is a problematic part in Mamba models. They have a way to solve it. We have in the CMamba a way to solve it. But here we see that this recurrent memory overflow problem, it also happens in short contexts that are shorter than the training length. So this is kind of a fundamental and different a limitation, and we need these like OPRM solutions that handle the information content and not just provide solution according to the amount of tokens that we want to process.
What if the context contains a lot of useful information, and you have to use a very small trunk size. And in that case, you don't have you don't have much benefit than the baseline transformer model.
Right. So yeah.
In terms of the total memory size, yeah.
Mm-hmm. Yeah, I totally agree. I think the main idea in this work is to kind of to understand what limits recurrent. If we always take the transformers and chunk and let them process, I think it will be a good solution. If we want to have recurrent models that, for example, it will be very interesting to understand why these recurrent states, their capacity is much smaller than expected because the hidden state is very large, but the capacity is still small. Our paper says that if you find a way to improve the utilization of the recurrent state, you will be able to get linear scaling for much longer chunks than ones of transformer. And also it says that you will also need to have this kind of aggregation method between these chunks. And we kind of had this feeling that if we are able to succeed in both axes, we will have much stronger recurrent models that will eventually have recurrent states that are larger than the chunks of the attention models before they reach the quadratic cost that starts to hurt us. So it's the method is not there yet, but the ideas are, let's see if this is a scalable paradigm. That's the motivation.
Yeah, agree. Do you have any speculation why desire model utilize those states very inefficiently?
My prediction is because how they are trained. We train these models to do language modeling. I don't know if this reinforces the creation of a large hidden state. So this kind of an idea I'm exploring now. I don't have any things beyond that, but I think I think this might be one of the reasons.
Yeah, thank you for your answer. Yeah, I don't have further questions. Do anyone have any questions? Feel free to unmute yourself or just leave the question in the chat.
Okay, so maybe I'll just jump to the recap if there's no more questions. So we saw that recurrent memory overflows, they are fundamentally a different limitation for long context processing of recurrent LLMs. And we saw that existing solutions, they kind of try to compress the whole context into a fixed size state, and this doesn't fully prevent recurrent memory overflows. We saw that our proposed method, OPRM, prevents recurrent memory overflows by dynamically allocating more recurrent memory. And we saw that this method, it's effective and efficient and general. It boosts performance on many models, also in real-world long context tasks. It runs faster than vanilla inference, and it's also training-free and architecture agnostic. So it's very easy to apply. If there's no more questions, then thank you. And if you want to check out the GitHub, the QR code. And also, I'd be happy if you have any ideas or want to chat, I'd be happy to.
Okay, seems that we do not have further questions. Maybe we can wrap it up here. And thank you again for the talk. I'll stop recording.